Hello friends and my dear students, I welcome you all to my channel. I hope you are all doing well and your studies are also going on well. This is part 2 video of the chapter of symmetry where I will discuss about the rotational symmetry, the figures that have a rotational symmetry and the order of rotational symmetry. In the previous video part 1, I discussed about reflection symmetry and solved the problems of exercise 18a. In this video, I will also solve the problems of the next exercise, that is exercise 18b, which is based on both reflection symmetry and rotational symmetry. So this video is part of the playlist CBSE Maths for class 7 following the textbook of author RS Aggarwal. If you are new to my channel or not yet subscribed, or if you are visiting my channel for the first time or this is your first video you are watching, then I strongly suggest and request that you support me by subscribing to my channel, and also do not forget to press the bell icon so that you will be notified by my future videos. So let's get started with this video. Okay, so I have my quick notes about the rotational symmetry that I will discuss in this video, and on the right hand side I will do the discussion and we will solve the problems of exercise 18b. But before I start rotational symmetry, I would like to clarify one thing regarding the reflection symmetry that I was discussing in the previous video. I said something wrong. One concept that I was discussing, it was wrong, and I said that, so what is a reflection symmetry? A reflection symmetry is a symmetry about a line where a figure is said to have like reflection symmetry about a line if the figure looks identical on either side of the line. Now I also said that, so let's say if this is the line, if this is a line of symmetry, let's say this is a line of symmetry. I'm taking a very let's say I'm taking a very basic example. Let's say this line of symmetry is let's say let's say this is a diagonal of a rectangle. Let's say I have a rectangle like this. I'm not sure how perfectly I will be able to draw. Let's say this is, and yeah. So let's say I have the rectangle ABCD. This is a figure rectangle ABCD, and I'm considering the diagonal AC as the line of symmetry. I discussed that. Let's say if the line AC, the diagonal, is the line of symmetry, can it be a line of symmetry? If this is a line of symmetry, then the part of the figure on both sides of the line of symmetry has to look identical. Now what exactly it means by look identical? It actually does not mean that both the parts or both the figures on either side of the line of symmetry has to be congruent. No, that is an incorrect description. Both the sides should look identical, meaning about the line of symmetry, if you take reflection of both the parts on either side. So for this line of symmetry, which is the diagonal AC of the rectangle ABCD, the part of the rectangle ABCD to the right hand side of the line of to the right hand side of the diagonal AC is triangle ACD, and on the right hand side, on the left hand side, the triangle is ABC. Now we know, it is clear, for any rectangle we will have triangle ACD will be congruent to triangle ABC. This is true, we know, but this does not necessarily mean that the AC, the diagonal AC, will be a line of symmetry, because the triangle ACD and the triangle ABC are not looking identical about the line, about the diagonal AC. What does it mean? What do I mean that they are not looking identical? Meaning, if you imagine, if you take the reflection of the triangle is ACD about the diagonal AC, let's say I have this diagonal AC. So we are considering the diagonal AC as the line of symmetry. Okay. Now I have this triangle. ACD on the right hand side of the diagonal AC, which we are considering to be the line of symmetry. Now, if so, the triangle ACD, its reflection about the diagonal AC has to be something like this. Let's say this is AEC. So we can see from the original diagram that the rectangle was ABCD, and we were considering the diagonal AC, which is vertical diagonal AC, and we are trying to see whether the diagonal AC can be a line of symmetry. Now, if diagonal AC, if the diagonal AC has to be a line of symmetry, then the triangle ACD, consider the triangle ACD, its reflection on the other side of the diagonal AC will be AEC. But in the original diagram, in the original rectangle, the triangle ABC is not same as triangle AEC. We can clearly, it is not looking same. They might be congruent, but they are not exactly same. So so that is the reason that the diagonal AC of the rectangle ABCD is not a line of symmetry. So both the diagonals of a rectangle, in any rectangle, the two diagonals are never a line of symmetry. In fact, in a rectangle, so the diagonals of a rectangle are never the line of symmetry. So in the previous video, I said that if any figure is symmetrical about a line, then that figure, the part of that figure on the parts of the figure on either side of the line has to be congruent. No, that is wrong. That is not wrong. That is wrong. That is a wrong statement. Congruency has nothing to do with the line of symmetry. The fundamental concept is that about the line of symmetry. So the line of symmetry will essentially divide the figure into two halves, and both the halves will be reflection of or mirror image of each other about the line of symmetry. So that is the correct way of saying. So similarly, I was saying the other day that the two diagonals of a parallelogram, of any parallelogram, are also a line of symmetry. That is false. That is false. If you consider the parallelogram A, B, C, D, the two diagonals AC and BD, they are not line of symmetry, because just consider the diagonal AC. If I extend it, if I consider this as a line of symmetry, let's say I am extending the diagonal AC and consider it as a line of symmetry, then the triangle ABC, which is on the right hand side of the diagonal AC, and above the diagonal AC, and the triangle ADC, which is below the diagonal AC, they are not looking identical. They has to look identical. There has to be mirror image. So for example, the mirror image of the triangle ABC above the diagonal AC will be something like, I may not be able to draw correctly, but something like this. AEC, the triangle AEC is looking identical to the triangle ABC, and they are mirror image of each other about the diagonal AC. And if you observe that the quadrilateral AECB will be a kite. Anyway, so this was one thing I wanted to clarify before starting rotational symmetry. Now let's start. What is rotational symmetry? So rotational symmetry is that, if the basic concept is that you have a figure, and that figure must have a center of rotation. So any figure, so if this is a, so I will discuss with the standard figures. So if it is a square, its center, this is the center, this is its center of rotation. So I will, if I will rotate the figure, the square, consider, imagine a vertical line, imagine a line passing through the center and which is perpendicular to this plane, to this plane ABCD, which is a square. Consider a line which is passing through the center O. What is the center of a square? If you join the two lines joining the midpoints of the opposite sides, their point of intersection is the center. If you consider, imagine a straight line passing through this point O and which is perpendicular to this plane of the square ABCD, about that line you will rotate the square. About that line you will rotate the square in the clockwise direction. So the rotation could be, so this is how you will rotate the figure. Now the definition says that a figure is said to have rotational symmetry if it fits onto itself n times, where n has to be greater than 1, n times during a whole rotation. So if you start from its initial position, whatever this figure be, I am considering a square, it could be a triangle, it could be a rectangle, it could be a parallelogram or any other figure. If you rotate that figure about its center in anti-clockwise direction, if you are rotating the figure and at any particular angle of rotation, if you see the figure, the position of the figure is exactly fitting the figure where it started, then that will be considered an angle of rotational symmetry. An angle of rotational symmetry. So this angle of rotational symmetry, it may be more than 1. It can be 2, it can be 3, it can be 4, but it has to be more than 1. So now, a figure is said to have rotational symmetry if it fits onto itself. If it fits onto itself means when you are rotating, after giving a certain rotation, whatever the position orientation of the figure is, if it exactly matches with the starting orientation and position of the figure, that is what it is. That is what it means, fits onto itself. So if it fits onto itself while you are rotating the figure, so you will rotate the figure maximum by 360 degree. So while you are rotating the figure by some angles up to 360 degree, and during that rotation, if you see that at n number of angles of rotation, the figure is perfectly matching with its original orientation and position, then this n is known as the order of rotational symmetry. And also, if n is greater than 1, then it is said that that figure has a rotational symmetry. Okay, so now let's discuss some of the standard figures that have rotational symmetry. The first one is equilateral triangle. So you need not take, I have tried my best to visually show how the figures are rotating by some angle, and how at certain angles of rotation the figure is fitting onto itself perfectly. I will attach a link of the PDF of these notes in the description below, so you need not take any screenshot from the notes. So in an equilateral triangle, you know, if the equilateral triangle is ABC, so we have an equilateral triangle. Now on the right hand side, I will not be able to draw perfectly. I am trying my best, but it may look very odd anyway. So if this is considered that this is a equilateral triangle, and we know that an equilateral triangle has 3 lines of symmetry, and those 3 lines of symmetry are the angle bisectors. So like this is the angle bisector of B, angle B, this is the angle bisector of angle C, and this is the angle bisector of angle A. So this if they intersect, they will intersect at a certain point O. So this is an equilateral triangle, they will intersect at a point O. So AO, BO and OC are the 3 lines of symmetry. Now And also you know that these angles, the angles between the lines of symmetry is 120 degree. It is 120 degree. Now, if you rotate in the diagram, in the notes, I have represented the rotation of this triangle at clockwise about the center of its figure, about its center, that is the point O, as like this. This means I am rotating the triangle clockwise by 120 degree from its starting position. So this is the starting position. If I do this after this rotation, the triangle will look exactly the same, but as you can see, the position of the vertices will change. This will be A, this will be B, and this will be C. But you can see that it is looking exactly identical to the starting position and orientation of the triangle. So after giving a rotation of 120 degree about its center, we see that the triangle we are getting is same, is identical, looking identical to the triangle from the starting position and orientation. So this is the angle 120 degree is a angle of rotational symmetry. Is an angle of rotational symmetry. Now again, if let's say this is the starting position of the triangle, and this is the position of the triangle after giving a rotation of 120 degree. Now if I rotate again the triangle at position 2 clockwise by 120 degree, I am rotating the triangle at position 2 by 120 degree, but actually I am rotating the triangle from its starting position by 240 degree. So in the notes I mentioned 240 degree. That means that it is an angle of rotation from the starting position. So after this, the triangle will look exactly the same. But as you can see, the position of the vertices will change. This will become A, B, C, but it is looking exactly like the position and orientation of the orientation of the triangle of the triangle in the initial position, that is position number 1. So if let this position be 3, so this triangle is also at position 3, which is the position or orientation of the triangle after giving a rotation of 240 degree from the initial position. So this is also angle 240 is also an angle of rotation. Okay. Now again, if you rotate the triangle at position 3 by 120 degree, that is, you are actually rotating the triangle from its initial position by 360 degree. 240 plus 120 is 360 degree. 360 degree, you will get back the original triangle. That is A, B, C. So this triangle at position 4 is also looking exactly identical to the triangle in the initial position, that is at position 1. So how many times so this angle 360 degree is also an angle of rotation. So we see that the first angle of rotation after which the triangle was looking identical to the initial triangle was 120 degree, and then at an angle of rotation of 240 degree, the triangle again was looking identical to the triangle in the initial position, that is position number 1. And after 240 degree rotation, the position of the triangle was position 2. Position was position 3. And then again, after an angle of rotation of 360 degree, the triangle was looking exactly the same. After 360 degree, the position of the triangle was 4. So we see that, and we will only consider of only a single rotation. A single rotation means a rotation of total rotation of 360 degree. So you can see that we are getting three angles of rotation, uh, which means at these angles of rotation, the triangle was looking identical to the triangle in the initial position or initial orientation. So since we have three angles of rotation, the order of rotational symmetry of an equilateral triangle I am considering as I am denoting with the letter n. N is 3. So if you rotate a figure, keep on rotating a figure up to 360 degree, that is up to a full rotation, and if you notice and if you mark and if you observe those angles of rotation at which the figure is looking exactly identical to the figure in the starting position, and if there are n number of those angles, then the order of rotational symmetry of that figure is n. So in an equilateral triangle, n we can see is 3, that is the order of rotational symmetry is 3, and the angles of rotational symmetry are 120 degree, that is after an initial rotation of 120 degree, the triangle will look exactly the same as its initial position, or at position 120 after a rotation of 120 degree, whatever the orientation of the triangle will exactly fit the orientation of the triangle at the beginning. Again, after 240 degree of rotation, we will see the triangle is obtaining an orientation which will exactly fit the orientation of the triangle at the beginning, and again at 360 degree we will see the same thing. So for an equilateral triangle, the order of rotational symmetry is 3, and the angles of rotational symmetry are 120 degree, 240 degree and 360 degree. Okay, I hope I am able to explain it properly, and if you think if you have any issue or difficulty in understanding, you can always you can always comment me, and I will try my best to address your query. So this was equilateral triangle. Let's see what about square. So a square, let's understand what are the angles of rotational symmetry of square, and what is the order of rotational symmetry. So in a square, it is very easy to understand that in a square now, so in a square definitely a square has 4 lines of symmetry, that is the 2 diagonals and the 2 sides joining the midpoints of the 2 opposite sides. So let's say these are 2 lines of symmetry which are the lines joining the midpoints of the 2 opposite sides. Now if I rotate, so let's say this square is A, B, C, D. Now if I rotate this square by 90 degree clockwise in the clockwise direction, the square will look exactly the same. The square will look exactly the same as the square in position 1. This is position 2, but notice it will look exactly the same, but actually the position of the vertices will change. So what will happen? This will be A, this will be B, this will be C, and this will be D. So we have rotated the square 90 degree clockwise, and we will have in the position 2 it will be its position, and we can see that clearly the square is looking identical. So the square at position 2 is also looking identical. So in the notes I have indicated with the right sign that it is looking identical to the square, to the figure at the initial starting position, and wherever you will see a cross somewhere beside the figure, that means that it is not identical. It is not identical to the figure in the starting position. Okay. So at position 2, we can see the square is looking identical to the square in position at position 1. Now if I again, so this was at position 2, at position 2 the square has been rotated 90 degree clockwise. Now if I rotate the square in position 1 180 degree clockwise, 180 degree clockwise, it will again look exactly the same. It will again look exactly the same, but definitely the position of the vertices have changed. So this will be B, this will be A, this will be C, and this will be D, and it is looking exactly the same as the square in position 1. So 90 degree is an angle of rotational symmetry, then 180 degree is another angle of rotational symmetry. Now remember that whenever I am drawing an arrow and above that I am saying 180 degree, it means that the figure in position 1 has been rotated by 180 degree. Okay, so this was position 3. Now if I from position 3, now if I rotate the square in position 1 by 270 degree, then by 270 degree, then also I will get the square which will look exactly the same, but definitely the position of the vertices have changed a bit. So this will be A, B, and C and D. So this is also this is position 4. This is also looking exactly the same as the square in position 1. So angle 270 degree is also an angle of rotational symmetry, because if the square in position 1 is rotated clockwise 270 degree, then it is looking exactly the same. And finally, if we rotate the square in position 1 by 360 degree, then we are also getting the square which is looking exactly the same as the square in position 1, but the position of the vertices or the corners will change. This will be basically now at position 5, the square is exactly the same as the square in position 1. So this square in position 5 is also looking identical to the original square, which is the square in position 1. So how many right signs you see? You see 4 right signs. And how many angles of rotational symmetry we see? The angles of rotational symmetry are 90 degree. So after a 90 degree rotation, we see that the square is looking identical. Again after 180 degree, we are seeing the square is identical. Similarly, after 270 degree and finally 360 degree, we are seeing that at these angles of rotation, 90 degree, 180 degree, 270 degree and 360 degree, the square looks identical to the square. The squares in all these, after all these angles of rotation, the squares are looking identical. So we have 4 angles of rotational symmetry, and hence the order of rotational symmetry n is 4 for a square. Okay. Now let's see what is a rectangle. Now I will not draw the rectangles on the right hand side from the notes. Let me see if we can see the notes properly. Okay. Let me discuss. I will discuss with reference to the notes. So you can see the rectangle is initially horizontal. By that I means the larger side is horizontal. So we have the rectangle ABCD. After it's rotated, I have visually given the different colors to the 2 lines of symmetry of the rectangle. So our rectangle has 2 lines of symmetry, which are the lines joining the midpoints of the opposite sides. So as you can see, one line of symmetry, the smaller line of symmetry is colored green and the larger line of symmetry is colored blue. So if it is given a 90 degree rotation clockwise, we see that the rectangle we are getting, it is not identical. So so after 90-degree rotation, we are not getting an identical rectangle. So 90-degree is not a angle of rotation, rotational symmetry. But if you see, if the rectangle is given a 180-degree rotation clockwise, we see the third figure, the rectangle is looking identical to the rectangle in the first position. So 180-degree is an angle of rotational symmetry. So clearly you can see that 180-degree and 360-degree are the two angles of rotational symmetry for a rectangle, and hence the order of rotational symmetry is 2. Okay. Now see a letter H. There are many letters from English alphabet which have rotational symmetry. I am only discussing letter H. So I have you can see the letter H. I have marked all the I have given some points, some markings to the end points and the points of intersection of the sticks or sides of the letter H, so that we can visually understand the orientation of the letter H when it is being rotated. So after when it is rotated 90-degree, we see that the letter H, so initially the letter H was vertical, the letter H has become horizontal, so definitely it is not looking identical. But after a 180-degree rotation clockwise, you can see the letter H is again looking identical. So 180-degree is a angle of rotation. But as you can see from the figure, the positions of the end points and the points of intersection of the letter H have changed. But it is looking identical. It is looking identical, meaning the letter H in position 3 will exactly fit the letter H in position 1. So again, if you give a 270-degree angle of rotation from the initial position, then again the letter H becomes horizontal, which is not looking identical. And finally, if you give a 360-degree angle of rotation clockwise, you will see the letter H is again looking identical. So for the letter H, 180-degree and 360-degree are the angles of rotational symmetry, and hence the order of rotational symmetry N is 2 for letter H. Now there are some other letters which also have some rotational symmetry. For example, let's say the letter I. The letter I. A letter I has two lines of symmetry. This is a one line of symmetry, and this is another line of symmetry. Now, so if you rotate the letter I 90-degree clockwise, you will see that the letter I has become like this, which is not looking identical. So this is not looking identical. But again, if you rotate the letter I from its initial position by 180-degree, you will see that now this arrow and this 180-degree, it means that after rotating the I in the initial position from the initial position by 180-degree clockwise, the position of the I will be back like this, and it is looking identical. But to give a clarification, please note that if I mark the points, let's say this point as A and this point as B, after a 90-degree rotation, this has become, this is point A and this is point B. And after a 180-degree rotation, you will see that this point is A and this point is B. The position of A and B has changed, but it is looking, anyway, the letter I is looking identical with the original letter I. So 180-degree is a angular rotational symmetry for letter I. So again, if you give a total angular rotation clockwise by 270-degree, you will again see the letter I has become like this, which is also not looking identical. And finally, if you give angle a rotation of 360 degree clockwise, then again you will see that the letter I is looking identical, and this time it is exactly the same as the original I. So this is angle of 360 is an angle of rotational symmetry. So for I, n is equal to 2, that is there are two angles of rotational symmetry. The first one is 180 degree and the second one is 360 degree. And so the angles of rotational symmetry for the letter I are 180 degree and 360 degree. Okay. Now there are some other letters. I will not discuss all of them. I hope you can figure it out by, you have to do a little bit of observation, and you have to draw the figures, draw the letters and figures, and see what is happening after rotating the figure by 90 degree, 180 degree, 270 degree and 360 degree. But it will not always be like 90 degree, 180 degree, 270 degree. It can be, it depends on the figure, and if the figure has any lines of symmetry, if the figure has lines of multiple lines of symmetry, and it will depend the angle between the lines of symmetry of a figure. If the angle between if a figure has two lines of symmetry, and if the angle between the two lines of symmetry in a figure is 90 degree, then quite possibly you will rotate the figure each time 90 degree to see whether it is becoming identical or not. For example, in the equilateral triangle, the lines of symmetry, they are 120 degree apart. So that is the reason we were rotating the triangle. If we rotate the triangle by 120 degree, we will observe angles of rotational symmetry. Okay. So this was letter H, and I also discussed letter I. Okay. Now so there are some figures which have both a line of symmetry and which both have reflection symmetry and rotational symmetry. For example, an equilateral triangle. An equilateral triangle, we know that there are three lines of symmetry, which are the angle bisectors. That is, the bisectors of each angle of the three angles of a triangle, of an equilateral triangle, they are the three lines of symmetry. And also we have seen that an equilateral triangle has three angles of rotational symmetry. They are 120 degree, 240 degree and 360 degree. Okay. So an equilateral triangle has both lines of symmetry, that is have both reflection symmetry and rotational symmetry. Squares also we have seen that a square has four lines of symmetry. That is, it has definitely reflection symmetry, and there are four lines of symmetry. Two are the diagonals, and other two lines are the lines joining the midpoints of the opposite sides. And also we have seen that a square has four angles of rotational symmetry. They are 90 degree, 180 degree, 270 degree and 360 degree. So the order of rotational symmetry of a square is 4. For a rectangle, the rectangle I have discussed that, I think I have discussed rectangle. No. Yes, in the notes, as you can see, a rectangle, we have seen that the rectangle also has two angles of rotational symmetry. They are 180 degree and 360 degree. So the order of rotational symmetry of a rectangle is 2. And also we know that the rectangle has two lines of symmetry, which, as you can see, are highlighted with green and blue color. They are the lines joining the midpoints of the opposite sides. So a rectangle has two lines of symmetry, and its order of rotational symmetry is 2. For a rhombus, we know a rhombus has two lines of symmetry, which are its two diagonals. The two diagonals of a rhombus are both the diagonals of a rhombus are a line of symmetry. And also a rhombus, let me discuss the rhombus. So a rhombus is a quadrilateral having all the four sides are equal and the diagonals bisect each other at 90 degree. So a rhombus can look like, let's say, like this. My diagram may not look perfect, but I am trying my best. So this is a kind of rhombus. A, B, C, D. So the lines of symmetry of the rhombus are the two diagonals AC and BD. AC and BD are the two lines of symmetry of the diagonals of these rhombus. Now let's understand about the rotational symmetry of the rhombus. So if you rotate the rhombus clockwise by 90 degree, the rhombus will look like something like this. So it will be A, B, C, D, and these are the lines of symmetry. And we can clearly see that this was the rhombus, the initial position of the rhombus, position 1. In position 2, we can clearly see that the rhombus is not looking identical. So this was the position 2 is the rhombus after an angle of rotation of 90 degree clockwise. Now if I rotate the rhombus from the starting position, position 1, by 180 degree, by 180 degree, we will see that the rhombus will look identical, even though the position of the vertices has changed, but the rhombus will look identical. So this is A, B, C, D, and these are the lines of symmetry, and this is looking identical. So position 3, the rhombus is looking identical to its original rhombus, that is the rhombus in position 1. So we see that the first angle of rotational symmetry is 180 degree. So similarly, after rotating the rhombus 360 degree, you will again see that the rhombus is looking identical. So for a rhombus, N is 2, as the angles of rotational symmetry are 180 degree and 360 degree. Now the letters HIOX, so these are all the figures which both have lines of symmetry as well as rotational symmetry, that is they both have reflection symmetry and rotational symmetry. Okay. So we discussed about equilateral triangle, squares, rectangle, rhombus. Now circle. A circle, as you can see, a circle. Now what are the lines of symmetry of a circle? We have already discussed in part 1 that any diameter, you consider any diameter of a circle is its line of symmetry. Now how many diameters are there in a circle? There are unlimited number of diameters in a circle. If you consider the center of the circle as O, then you can basically there are unlimited number of points of the circumference of a circle. Now if you draw the line from the center O, if you consider a point on the circumference of the circle, let's say A, and so if you join OA and if we extend it, and let's say OA is intersecting the circle at other point, let's say A dash, then definitely A dash is a diameter of the circle and it will be a line of symmetry. But since there are infinite number of points, let's say there is another point very near to the point A on the circumference of the circle, let's say it is B, another point C, D, this way A, B, C, D, there will be unlimited number of points. So for each of those points you can draw a different diameter of the circle. So there will be unlimited number of diameters. So hence a circle has unlimited number of lines of symmetry. And also you can observe, you can understand that if you rotate the circle about its origin by any angle, any small angle, any very small angle, it will look the same. It will be the circle. It will be identical. So So you can say that n for the order of rotational symmetry for circle will be actually be infinity. Infinity, even though this circle is not discussed in the book, but this is my concept, my understanding, that the order of rotational symmetry for a circle will be infinity, unlimited, or infinity. I mean a very very large number, since I can rotate the circle at a very very small amount, at very very small amount, at very very small amount. Now remember that the definition of rotational symmetry says that when you are rotating a figure about its center until full rotation, that is, you are rotating the figure uh, slowly until you are reaching an angle of rotation of 360 degree. So, in between, at any angle of rotation, if the figure is looking identical, then that angle is a angle of rotational symmetry. For a circle, as you can see, if I rotate the circle by let's say I am rotating, let's say this is another diameter which is horizontal. Let's say this is another diameter. Let's say POQ is another diameter. Now, if I, let's say, rotate this circle by a very tiny by an angle theta clockwise, so let's say, and the diameter PQ now becomes P dash Q dash. I have rotated the circle by a very small angle theta clockwise. So now the position of the diameter PQ has become P dash Q dash. Theta is very small. Now consider. Now this theta I can take very very small, very very small, and still whatever this for any value of theta, the circle will look identical. So how many rotations can I make? How many rotations can I make until a full rotation is complete? That will be 360 degree by theta. And if I take theta very very small, theta, if theta is very small, this will imply 360 degree by theta, which is actually will be very large, So this is the reason, this is the concept based on which I am saying that the order of rotational symmetry of a circle is infinity, that is n will be very very large. As you can see, actually n will be 360 by theta, where I can consider theta to be very very small angle, Okay. So that was all about the rotational symmetry. I have discussed some figures which both have lines of symmetry and rotational symmetry, and I discussed about the figures having rotational symmetry like letter H, rectangle, a square, and equilateral triangle. So I hope these notes, whose link will be in the description below, this will give you a better insight of how the order of rotational symmetry and the angles of rotational symmetry are being obtained for a given figure. Now let's try to solve the problems of exercise the 2b. Which exercise is this? This is 18b, sorry. So let's now solve the problems of exercise 18b. I hope you can see the problems. Okay. So let's solve exercise 18b. Problem number 1, part 1 says, how many lines of symmetry does an equilateral triangle have? Obviously 3. 3 lines of symmetry. Lines of symmetry, I mean short writing LOS. And these lines of symmetry are angle bisectors of 3 angles of the equilateral triangle. Okay. And part 2 says, what is the order of rotational symmetry of an equilateral triangle? We have already discussed. N will be 3, and the angles of rotational symmetry are 120 degree, 240 degree, and 360 degree. From the angles of the rotational symmetry, you will directly get the value of n, that is the order of rotational symmetry. If there are n number of angles of rotational symmetry, which means the order of rotational symmetry is n. Okay. Problem number 2. Through what different angles should a rectangle be rotated to be in symmetrical position with the original position? So I have already discussed about a rectangle, a rotational symmetry of rectangle. So n we know is 2, and the angles of rotational symmetry are 180 degree and 360 degree. For a rectangle, if you rotate the rectangle by 180 degree, then it will look identical. Again, if you rotate the if you rotate the angle by 360 degree, it will look identical. So 180 degrees, there are two angles of rotational symmetry. They are 180 degree and 360 degree, and since there are two angles of rotational symmetry, the order of rotational symmetry is 2 for a rectangle. Problem number 3. What is the order of rotational symmetry of a square? Give the angles of such rotations. Definitely, the order of rotational symmetry for a square is 4, as there are 4 angles of rotational symmetry. The first one is 90 degree, the second one is 180 degree, again 270 degree, and finally 360 degree for a square. Okay. Problem number 4, part 1 is, how many lines of symmetry does a rhombus have? A rhombus have 2 lines of symmetry, and they are the 2 diagonals. The 2 diagonals of a rhombus are its lines of symmetry. Okay. And part 2 is, for a rhombus, what is the order of rotational symmetry of a rhombus? N equals to 2, as we have seen that, and angular rotational symmetry are 180 degree and 360 degree. So we have discussed in rhombus, as you can see that in the rhombus, if I rotate by 90 degree, then it is not looking identical, but if I rotate by 180 degree, it is looking identical. So hence, again, if I rotate the rhombus by 360 degree, it will look identical. So for a rhombus, the 2 lines of symmetry are its 2 diagonals, and it has order of rotational symmetry is 2, and the angles of rotational symmetry are 180 degree and 360 degree. Okay. Problem number 5. Write 3 letters of the English alphabet which have 2 lines of symmetry and rotational symmetry of order 2. Okay. So rotational. So I is one letter. I has. So let me. It has asked write 3 letters of the English alphabet. So first one is definitely the letter I. As you can see, this is one lines of symmetry. It is asking which has 2 lines of symmetry. So this is one line of symmetry for an I, and also this is another line of symmetry of the letter I. And so the letter I, and we can clearly see if we rotate the letter I by 90 degree, initially it will look like this, which is not looking identical. And if you rotate the letter I by 180 degree, then you will see it will look identical. So this is not looking identical, this is looking identical. And again, if you rotate the letter I If you rotate the letter I clockwise by 270 degree, it will again not look identical. And again, if you rotate the letter I by 360 degree, then again it will look identical. So the angles of rotational symmetry for letter I are 180 and 360 degree. So n is 2, since it has two. N is order of rotational symmetry is 2, since there are two angles of rotational symmetry, 180 and 360. So letter I is 1. We have to find three letters. I think letter H, since letter H, for letter H, this is letter H. If you, what are the lines of symmetry for letter H? This line, this is one line of symmetry of the letter H, and another one is this one. This is also a line of symmetry for the letter H. And so this letter H has two lines of symmetry, and of course, since as you can see, the two lines of symmetry are at 90 degree, making a 90 degree angle to each other. So it is possibly at 180 degree. Let's see, if you rotate the letter H first by 90 degree clockwise, definitely the letter H will look like this, and it is not definitely looking identical. And if you rotate the letter H clockwise by 180 degree, then it will again look identical. And if you rotate the letter H by clockwise by 270 degree, then again it will look like this, which is not identical. And finally, if you rotate the angle, the letter H by 360 degree clockwise, you will get back the exact same letter H. This is looking identical. So angle 180 degree and 360 degree are the two angles of rotational symmetry. So definitely n is equal to 2, and the angles of rotational symmetry are 180 degree and 360 degree. So for letter I also, n equals to 2, that is the order of rotational symmetry is 2, and the angles of rotational symmetry are 180 degree and 360 degree. And both these letters I and H, they have two lines of symmetry. What else? We have to find three letters. What could be the third letter? A letter which has two lines of symmetry. Yes, the letter O, which is a kind of oval. Letter O, which is a kind of oval. And I don't think letter O is a square, is a circle. And clearly, oval has two lines of symmetry, this line and this line. Two lines of symmetry. And for this figure also, we can see that the two lines of symmetry are making an angle of 90 degree. So quite possibly the angles of rotational symmetry will be 180 degree and 360 degree. So now if you rotate this letter O by 90 degree clockwise, we see the letter O becomes like this, which is not looking identical. And if you rotate the letter O by 180 degree clockwise, it will look like this, which is identical. And again, if you rotate by clockwise by 270 degree, then again it will not look identical, it will look like this. And finally, if you rotate the letter O by 360 degree clockwise, then again you will see the exact same letter O. So 180 degree and 360 degree. So we can clearly see n equals to 2 and the angles of rotational symmetry are 180 degree and 360 degree. So we have letter H, I and O. There could be some other letters, but as far as my memory is concerned, I can think of letter I, H and O. Okay, let's do problem number 6. Give an example of a figure that has a line of symmetry but does not have rotational symmetry. So as in the hint is already given. As the hint is given, it is an isosceles triangle. Always remember that an isosceles triangle has a line of symmetry. Let's say if ABC is an isosceles triangle where AB is equal to AC and the angle between the two equal sides AB and AC is the angle A. So what is the line of symmetry for this isosceles triangle ABC where AB is equal to AC? That is the line of symmetry is the bisector of the angle A, the bisector of the angle which is included between the two equal sides. This is the line of symmetry, and let this line be intersect the opposite side BC at T. Then we know that AD will also be perpendicular to BC, and also AD will bisect the side BC. So AD is the line of symmetry. It has only one line of symmetry. That is the line which is the bisector of the angle which is included between the two equal sides of the isosceles triangle. So this is the line of symmetry, but you will see that this isosceles triangle do not have any rotational symmetry. That is, if you consider the center of the isosceles triangle as this, if you rotate this isosceles triangle by any angle, whatever angle you rotate, you will never find a position which is looking identical. I mean, after 360 degree, obviously the triangle will be back to its original position, but in that case n will be 1. But as per definition, n has to be greater than 1 for a figure to have a rotational symmetry. I mean, any figure, if you rotate any figure by 360 degree, it will obviously come to its original position and it will look identical. But in that case, n will be 1. But for a figure, if it has to have a rotational symmetry, n has to be greater than 1. So that is, we must find two such angles of rotation, minimum two such angles of rotational symmetry where the figure will look identical. And for an isosceles triangle, you won't find two such angles of rotation where it will look identical to the isosceles triangle in the first position. Okay, let's do problem number 7. Does every trapezium have a line of symmetry? No. What is a trapezium? A trapezium has two parallel lines, two opposite sides are parallel, and they are not equal, and so this is a trapezium where this is a trapezium ABCD where AB is parallel to CD and so this is a trapezium where only the two opposite sides are parallel. Now, does every trapezium have a line of symmetry? No. Only we have seen that only an isosceles trapezium has a line of symmetry. Consider this trapezium. Consider this trapezium AB, C, D. AB is parallel to CD, but definitely it has no line of symmetry. That is, you cannot draw any line where the trapezium ABCD it will look identical on either side of that line. But if only if the trapezium is an isosceles trapezium, meaning it is of where an isosceles trapezium is such that if ABCD is a isosceles trapezium where AB is parallel to CD, where AB is parallel to CD, and AD is equal to BC. So this is in this case in a trapezium where AB is parallel to CD and AD is equal to BC, then this is an isosceles trapezium. And this isosceles trapezium, any isosceles trapezium has a line of symmetry, which is the line joining the midpoints of the two parallel sides. So if E is the midpoint of side AB and F is the midpoint of side BC or CD, then EF, the line EF is the line of symmetry for the isosceles, these isosceles trapezium. As you can see, the figure EBCF is looking identical to the figure EADF. So only an isosceles trapezium has a line of symmetry. Problem number 8. What is the line of symmetry of a semicircle? What is the line of symmetry of a semicircle? So a semicircle is half of a circle. That is, it will look like this. So AB is the diameter of the semicircle, and let's say O is the center. So and let's say C is some point on the circumference. Then the figure ACB is a semicircle. The figure ACB is a semicircle. So what will be the line of symmetry for this semicircle ACB? It will be the line perpendicular to the diameter AB passing through the center O. This is the line of symmetry of the semicircle. That is the line which is perpendicular to the diameter AB and passing through the center O. So what is the line of symmetry of a semicircle? Does it have rotational symmetry? Does it have rotational symmetry? Semicircle. A rotational symmetry. It has only one line of symmetry. Now, only one line of symmetry. Any figure having only a single line of symmetry, can it have a rotational symmetry? No, I don't think so. Semicircle doesn't have any rotational symmetry. For this, n will be equal to 1, and the angle of, there will be only one angle of rotational symmetry, that is 360 degree. If you rotate the semicircle 360 degree, it will come back to its original position, and so 360 degree is the only angle of rotational symmetry, and so n will be 1, and hence semicircle do not have a rotational symmetry, as n has to be, for a figure to have rotational symmetry, n has to be greater than 1, at least n has to be 2. Okay, question number 9. Give an example of a geometrical figure which has neither a line of symmetry nor a rotational symmetry. It's you can consider any scalene triangle. Any scalene triangle do not have any line of symmetry, and I think it also do not have any rotational symmetry. So let's say this possibly is a scalene triangle ABC. This scalene triangle AB, where AB not equal to BC and also BC not equals to AC. So this implies also we know that angle A not equals to angle B not equals to angle C. In a scalene triangle, all the sides, the length of the sides of the length of all the sides, three sides are different, and also the angles are different. So this scalene triangle will never have any line of symmetry, and also it will not have any rotational symmetry as well. So I think a scalene triangle is an example. Question number 10. Let me zoom in. Question number 10. Okay. Question number 10, part 1. Find the number of lines of symmetry and the order of rotational symmetry of the adjoining figure. Draw the line of symmetry. Okay, what figure is given? Okay, so the figure given is something like we have this kind of figure going on. This is the given figure, and we are asked to find the line of symmetry and the order of rotational symmetry if there is. So clearly, if this figure is A, B, C, D, then the line joining B and D, the line joining B and D will be the line of symmetry for this figure. So BD will be the line of symmetry. As you can see, the figure, the triangle BCD and the triangle BAD are looking identical, meaning the triangle ABD, that is the triangle ABD and triangle BDC are a reflection of each other about the line of symmetry BD. So the if I name the corners, vertices of the given figure as ABCD, so the line joining the vertices or the points B and D will be the line of symmetry for this figure. Now we need to check whether this figure has any order of rotational symmetry or not. No, I don't think so. The order of what is the question? Draw the line of symmetry. The order of rotation. Find the order of rotational symmetry of the adjoining figure. Now, if we rotate, no, I think n for this will be the order of rotational symmetry. Now, the order of a rotational symmetry order. Does it have rotational symmetry? The order of rotational symmetry will be 1 because, and the angle of rotational symmetry will be 360 degree. If we rotate this figure by 360 degree, it will come back to its original position. Only then it will be identical. Any other angles, by any other angles, if you rotate this figure, it will not look identical. So only after rotating the figure by 360 degree, it will look identical. So 360 degree is only the angle of rotational symmetry. So in that case, n will be equals to 1. That is the order of rotational symmetry. But this figure n equals to 1 does not say that this figure will have a rotational symmetry, because rotational figure having rotational symmetry, the order must be greater than 1. The order must be at least 2. The order of rotational symmetry. I don't think there will be any angle of rotation other than 360 degree where the figure will look identical. Mm, If we rotate by 90 degree, it will look like this, and then again 90 degree will look like this. This, no, this figure is do not have any rotational symmetry first of all, and but it is asking the order of rotational symmetry. Now my question is, if a figure is not do not have rotational symmetry, then is its order of rotational symmetry 0, or is it for this figure, uh, as per definition, as per definition, uh, what the definition says that a figure is said to have rotational symmetry if it fits onto it itself n times where n is greater than 1 during a whole rotation about its center. N is called the order of rotational symmetry. Okay, I think the order of rotational symmetry will be 1, since only after rotating this figure by 360 degree it will come back to its original position and it will look identical. So n is equals to 1, that is the order of rotational symmetry is 1, but this figure is not do not have a rotational symmetry since n equals to 1. For a figure to have rotational symmetry, n must be at least 2. Okay, let's do problem number 11. So what was part 2? Part 1, the number of lines of symmetry is 1. So part 1 is 1 line of symmetry, and part 2, the order of rotational symmetry, in my understanding, in the order of rotational symmetry is 1, since at the angle of rotation of 360 degree it will look identical, but this figure will not said to have a rotational symmetry because n is 1, n has to be greater than 1. Okay, problem number 11. How many lines of symmetry does the given figure have? Draw these lines. So for a given figure we have to draw the lines of symmetry, and what is the order of rotational symmetry of the given figure. Okay, so the given figure is something like this. We have this, again this, my figure may not be exactly as the figure given in the problem, but anyway this is more or less the figure. So definitely we can say that if you mark the vertices, corners A, B, C, D, E, F, G, H, I, J, then the line joining the corners C and H, this line is one line of symmetry. This is one line of symmetry, and another line is if you join the midpoints of the sides AJ and EF. This is the, let's say this is P. Midpoint of AJ, the side AJ is P, and midpoint of EF is Q. Then if we join P and Q, this is another line of symmetry. This is another line of symmetry. So this figure has two lines of symmetry. How many lines of symmetry does the given figure have? So part 1 is 2 line of symmetry. Draw these lines. So I have already drawn the lines. One is the horizontal line, which is the line joining the midpoints of the two extreme sides, the vertical sides, and the another one is the vertical line joining the two corners that is the corners of the triangle shape, that is C and H, the line joining the C and H, that is the another line of symmetry. what is the order of rotational symmetry of the given figure. Okay, now if you see, uh, uh, let's say I am, for simplicity, for the sake of simplicity of drawing the figure, let's say I am approximately drawing this figure as like this. uh, I hope you will understand. Let's say this is the given figure. More or less it will look like this. So if I, so as you can see, if this is the approximately the figure, to see whether it has any rotational symmetry or not, we have to see, let's say if I rotate this figure clockwise 90 degree, how will it look? It will look like this. So this is not looking identical. Now if I rotate this figure clockwise 180 degree, how will it look? It will look like this, and hence it is identical. So 180 degree is one angle of rotational symmetry. And again, if I rotate this angle, this figure by 270 degree, I can see it will look like this. So this is also not looking identical. And finally, if I rotate the figure by 360 degree, we can see that it will again look identical. So 360 degree is an angle of rotational symmetry. So we can clearly see for this figure, n equals to 2. The order of rotational symmetry is 2, and the angles of rotational symmetry are 180 degree and 360 degree. Okay. Part 2, the order of rotational symmetry is 2. Question number 12. Give an example of a letter of the English alphabet which has no line of symmetry and rotational symmetry of order 2. Okay, so alphabet from the English alphabet, letter from the English alphabet which has no line of symmetry but rotational symmetry of order 2. A rotational symmetry of order 2. Rotational symmetry of order 2 letters, but it does not have any line of symmetry. What about letter N? N. The letter N has no line of symmetry. The letter N, as you can see, you will realize that the letter N has no line of symmetry. And if I rotate the letter N by 90 degree, what do I get? I get like this, 90 degree. Okay. Now if I rotate the letter N by 180 degree, what do I get? I will get this. Okay. So 180 degree is an angle of rotational symmetry. Okay. Now again, if I rotate the letter N clockwise by 270 degree, it will look like again like this. And this is not looking identical. This is not looking identical. And again, if I rotate the letter N clockwise by 360 degree, I am again getting this. This is looking identical. So 360 degree and 180 degree are the two angles of rotational symmetry for the letter N. So we can clearly see, we can consider the letter N, where order of rotational symmetry. The order of rotational symmetry clearly we see is 2, and the angles of rotational symmetry is are 180 degree and 360 degree. Okay, so this brings to an end of solving the problems of exercise 18B, which was based on the reflection symmetry as well as rotational symmetry. So I hope this video was beneficial in understanding the concepts of rotational symmetry and all the standard figures which have rotational symmetry and their order of rotational symmetry, their lines of symmetry, and so this part 1 and part 2 should give you a better good idea of the concepts of two types of symmetry, that is reflection symmetry and rotational symmetry, and all the common standard figures that have that have reflection symmetry, and what are the lines of symmetry, and the figures having rotational symmetry, and what is the order of their rotational symmetry. So if this video was beneficial, then please like it, share it with your friends, and once again please support me by subscribing to my channel, and do not forget to press the bell icon so that you will be notified by my future videos. So I think with this exercise 18B, it comes to an end of the chapter reflection and rotational symmetry. The next chapter, hope there is no other concept. Yeah, exercise 18B is the last exercise from this chapter, reflection and rotational symmetry. The next chapter is three-dimensional shapes. So the next video I will start three-dimensional shapes, but before that I will try to make two practice test paper, as I always do for every chapter. So I will try to make if not two, then at least one practice test paper that will be kind of MCQ questions, 15 questions or 10 to 15 MCQ questions that you need to solve in 45 or 1 hour. So before going on to the next chapter, I will prepare the sample test paper by tomorrow or day after tomorrow. So please stay tuned for the sample test paper 1 on the chapter of reflection and rotational symmetry. Then we will move on to the next chapter, three-dimensional shapes. So thanks for watching this video, and until the next video, take care and bye.